Yeah, we do.
Hey, everybody. Out there in Zoom world.
Let's see if Chris have a good night. Yeah.
How's it going, Chris?
It's going all right. How about yourself?
It's good. It's okay.
I heard about the news. I'm sorry for your loss.
Oh yeah. I mean, my wife's taking it really hard. She's had the cat ever since she was in 7th grade, basically. So
Yeah, it's. I mean, at that point, they're family.
she is. Yeah.
Hey, Dr. Tom.
Hey guys.
Do you know when you're posting the homework solutions? I got really frustrated on the last couple.
I usually post them after I grade them, so I'm probably gonna grade them on Friday. Because tomorrow I'm setting something up, and then for my research, and then I'll have more time on Friday.
Okay, sounds good.
I like the haircut. I didn't even recognize you.
Oh, yeah. I figured when you said, hey guys, you probably didn't recognize me. I got a cut on Thursday because I had that job interview on Friday.
That's right. That's right.
So I couldn't walk in with the ratty hair. So I had to go get it cut.
I recognize your voice, but then I didn't make the association with your hair and everything. I'm like, oh, it's Jacob.
Yeah, it's been a while since I've had my hair this short, but yeah. All right, Dr. Trent, I'm gonna go work on the new homework assignment, and then I'll have some questions after class.
Got it. Sounds good.
So they're gonna be a MATLAB class again, or?
No, it'll be mostly with the lecture.
Okay.
Yeah. I have one sample code that I posted online, but I'll run it in front of you guys. So
Okay. Sounds good. So I gotta get to work on your assignment. I'm getting ass blasted with labs.
Oh yeah, I know. That's kind of what it seems like for everyone right now. Is things are definitely heating up, and we're getting into midterm season too.
Yeah, I know. I was working a bit on the MATLAB assignment. I was just like, oh God, no. It's tricky. I'll figure it out. Your office hours are tomorrow. Are you going to be having them in person or through Zoom?
I'll have both, and so I'll be physically in my office, but I'll open up the Zoom room too. So I take answers from both.
Okay, cool.
Yeah. Mhm.
Charlie. I should have completely off. My kids and I were completely different. Like maybe more I was doing is completely wrong. So it's honestly that was
Excited for Elden Ring?
I've only heard about it. I feel like I'm so behind on gaming news nowadays. Like all my friends are into the new game Lost Ark.
Yeah, same for me.
Like all my friends have literally played probably 70, 80 hours already. I've only played it for 5 hours. I don't know, but they ask me every day if I'm level 50 yet because they want to dungeon together, but
Yeah.
I'm not even close.
Yeah, same with me. They try to get me into it, but I'm like, man, I got 6 classes. I barely got time.
Yeah, it's hard.
It
I wish I had more time in my life to because MMOs are really fun, especially when all your friends are.
Oh,
into it,
definitely.
but yeah, maybe I'm past that age in my life.
Oh, it still is. I mean, my group of friends are all in the MMOs. They keep playing Final Fantasy
Mm.
and at least Lost Ark now. Me, I tried to get into it, but I just didn't. Lost Ark, I played a bit. I kind of like it.
Mhm. Yeah, it's fun. It's just it's just a lot of time.
Yeah.
Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. This is the first and last time I'll be seeing you this week because we had a holiday on Monday. So how's everyone doing? How's everyone doing today? Stress? Yeah, I know. It's that time of the semester. I know everything's ramping up, and you know, yeah. Unfortunately, that's just how kind of classes are. Everything kind of just kind of wombo combos you at the same time, like midterms, labs, and everything. So just hang in there, guys, and hopefully you guys will all get through it. Okay, and so not to be the bearer of more bad news, but we do have a midterm in this class as well. But it's not going to be for 2 weeks, and so the midterm is planned for Wednesday. I believe that's March 9th. Okay, and so I do want to go over some of the logistics of the midterm because we are on schedule, and so usually I don't announce the midterm date. I know I have the dates in the syllabus, but sometimes I have to push it back just depending on how the class is going. But we are pretty squarely on schedule for this class, so I'm confident we can make that date. Okay. So first of all, we talked about this at the beginning of the semester, but the exams are going to be in person, and so everyone has to show up to the classroom for it. So everyone that's on Zoom, make sure you have plans to come to campus on Wednesday, March 9th. Okay. Okay. In terms of what you can bring to the exam, I have the same policy for all my classes. And so you're allowed to bring a single 8.5 by 11 sheet of notes.
One side or two?
Both sides. Okay. Okay. So I think you guys are past the point in your life where you have to memorize stuff for your classes, and so I think the conceptual understanding and the algorithms for this class are difficult enough, and so I want to give you guys that sheet of notes that you can write down just whatever you feel like you need for the exam. I don't like to give open book, open note exams. I know that was kind of the norm during virtual instructions, but I think what tends to happen is that it kind of lures people into a false sense of security. Because you feel like I can always look things up in the notes, and so with the one sheet of notes, what my hope is that you guys kind of spend the time to actually condense a lot of the information we've learned so far into that sheet of notes, and that by itself is already a great study tool. Okay, because I've seen it happen, both in the classes I've taught and classes that I've been a part of with my friends, where it's like an open book exam. I've even had a programming class which was open computer, and so you can just freely Google stuff or run stuff like the MATLAB codes and stuff. And I've never seen a lower test average than on that exam. That was open everything, just because everyone felt like I can just run my code on my computer and just check it. What happened was that people only finished about like 30% of the exam by the time it was over, and so. And then of that 30% that they finished, they only got half of it right. And so the average was like 20-something%, which is really kind of crazy. And I don't know if that professor was trying to make a point, but he never did that again. Anyway, what else? Okay, study guide. And so I'm going to put out a study guide next week. And so you can expect that probably early next week. Okay. And the purpose of the study guide is to guide your studying. And so it's a condensed list of topics that you can use to study for the exam. Okay. So I always like to put that out. And one other thing that I provide for exam prep is a review video. Okay. So this is a video that I record just in my office, and so this is asynchronous. Usually I take about an hour. Okay. And I use that video to review a lot of the key concepts, you know, that are going to be covered on the midterm. Okay. But you know, even though an hour is a decent chunk of time, it's not enough time to cover everything that we've covered so far. And so what I do is that what you'll see next week is I'll put out a poll on Canvas where you can vote on the topics that we've covered so far that you feel most uncomfortable with, that you feel like you need a little bit more review. And so based on the top two entries in that poll, then that's what I'll choose to review in the video. Okay. And then that'll be posted next Friday. Fridays are just the times that I have the most free time. And so that's when I can sit down and record these things. Okay. All right. And so that's the midterm. Okay. In terms of content that I've assigned, it's going to cover content from homeworks 1 through 3. Okay. And so I believe you guys are just finishing up homework 2 just today. And there's one more homework that I'm going to post based on the convection stuff that we'll cover today and Monday. Okay. And so that's going to be due next Friday. And so you can expect the convection stuff to be on the exam as well. Okay. So one thing I always tell people is that, you know, the homeworks, I make up all my homework problems and I make up my exam problems. And so, you know, if you kind of get used to the style of the homework problems and you can answer them really well, then you'll be in great shape for the exam. Okay. And reviewing homework problems, there's an effective way to do it, to make sure you get the most out of it. Because, you know, by the time you're probably going to sit down and study, I'll have posted all the solutions for homeworks 1 through 3. And so what people tend to do is that they kind of just look at the homework solutions and just read it and then just think, oh yeah, you know, I got this, no problem. But I think the best way to study homework problems is to try to redo them from scratch, because on the exam, you know, you're going to be faced with all fresh new problems. Like even if you put the homework solutions on your cheat sheet. And so getting used to, you know, taking a problem from scratch and working it through like that, that's kind of, you know, that's kind of giving your mind the practice of being in that exam environment. And so, you know, at least try to work through the problems, you know, from scratch first, and then check the solutions after. But don't use the solutions until you've actually tried the problems for good when you're studying. Okay. So that would be my advice for using the homework problems to study. Okay. All right. And so I think that's all the logistical information about the exam. So are there any questions about any of this?
Is exam going to be related to MATLAB?
Right. So good question. So the question is the exam going to have any MATLAB? So no. And so the way the exam is going to work is going to be very similar to like all the homework problems where I ask you to derive the algebraic equations. And so basically every single exam problem is going to be, I'm going to give you a differential equation. It's going to have some diffusion. It's going to have some convection, and I want you to derive, you know, what the governing algebraic equations are for them. Yep. So I'll have some 1D problems. I'll have some 2D problems, you know, and then kind of everything in between there. Yeah. Right. So no.
Another quick question.
Yeah.
Will there be a response?
Yeah. So the question is, will there be free response questions? Yes, there will. And so that'll be 40% of the exam. 40% will be like conceptual, like short answer questions. Yeah. Mm-hmm. Okay. All right. Any other questions from Zoom people about the exam? Okay. All right. And so, all right. And so the exam is going to be in 2 weeks. And so, you know, there's still time to prep, and there's still more that we need to cover. And so let's go ahead and cover the last kind of big topic that's going to be on the exam, which is convection. Okay. And so convection here is a whole nother type of physics that we're going to be simulating. Okay. And so far all we've covered is just diffusion, right? Okay. And so we basically just looked at equations that look like this, right? Let me just do the 1D case for now. Okay. So this is for 1D. Right. And so remember, diffusion is characterized by a second order derivative. Okay, and so that's what we have here. So this term right here is our diffusion term. Okay. And this term right here is kind of loosely characterized as like a source term. Okay. So all we've done so far, we spent a week to cover 1D problems. We spent a week on 2D problems as we learned how to solve these kinds of problems using finite differences. Okay, and all that we did was we took this derivative, we replaced it with the finite difference approximation, and then we formed our algebraic equations from that. Okay, and so starting this week, we're going to be adding a new term to it. Okay. And it's going to take this this form. Okay. And so we're going to be adding a first order derivative to our expression here, and that first order derivative is going to represent convection. Okay. And so what we're going to do today is we're going to explain conceptually what convection is, what it physically represents, in terms of transport. And then we'll talk about some of the numerical some of the numerical issues that comes with trying to solve this using finite differences. Okay. Okay. Any questions on this? Okay. All right, so just like before. We will solve finite differences. Okay. And so remember, what finite differences means that we're going to take those derivatives, replace it with an algebraic expression, and then use that to derive kind of a system of linear algebraic equations that we can solve. Okay? But before we do that, because what you'll see is that there are some new, I'll call them issues with convection that we didn't see before with diffusion. Just so that we can kind of understand what those issues are. Let's talk about kind of what convection physically means. Okay? Okay. All right, so the definition of convection, and this is something you can look up in a heat transfer textbook or even in fluid mechanics textbook, is the transport of some physical quantity through a moving fluid. Okay. And so one example that's I think kind of easy to understand is if you have like a fan, right? And so let's say that you have a room fan. Okay? Okay. And this fan is rotating around. Okay. Let's say that it's sitting on the ground, and this fan is going to cause an airflow, in one direction. Okay. Okay. Right, and so you have a kind of a one direction of wind, that's going in one direction. Okay. So let's say that you took a can of air freshener. Okay. Let me use blue. Right, so here you have like some Lysol spray or whatever frou-frou stuff they sell at Target nowadays, right? And so let's say that you spray some of that air freshener into the fan, right? And so what do you expect to happen to that air freshener particles? Let's call it particles, right? Or the smell, right? And so what we expect to happen is that once you spray the Lysol into the fan, then the air current that the fan is producing is going to take that air freshener, okay, and then blow it down downstream, okay. Okay. Right. So the key word that I want to define here is downstream, and that's a term that I'm going to use later on as well. Okay. And so when you have kind of a directional fluid flow here, whether it be air or whether it be water, right, or any other fluid, right? When you refer to the downstream direction, that refers to the place where the fluid is flowing to, right? And so since this fan is blowing air from the left to the right, we're going to call the right direction or anything towards the right downstream. Okay. And then the direction that's opposite to the fluid flow, and so let's say that we're going back towards the fan, we're going to call that upstream. Okay. Okay. And so that's what happens when you have convection, right? And so when you have convection, the fluid is flowing in a particular direction, and then just stuff is going to be transported with that airflow. Okay. And so let's contrast this case for what happens if we have just diffusion. Okay. And so without if you don't have any airflow, and you spray, let's say we're in this room, and I know there's a small current, there's a small airflow going on right now. But if I took a bottle of Lysol and just sprayed it, right, even in the absence of airflow, right, even someone in the back of the room, they can expect to eventually get the air freshener smell, right, even with the absence of airflow. Okay. And the way that happens is through diffusion, right? And so if we kind of illustrate that fact. Right, so let's say that we spray air freshener into a certain location, right? What we expect to happen in this case is that the air freshener is going to slowly kind of spread out to the entire room, right? Okay. And so this spreading, and some people even call it passive spreading because there's nothing forcing it to happen. It just kind of naturally happens on its own. This kind of passive spreading in all directions, this is what's known as diffusion. Okay. And that's what we've been modeling so far. And so far, in this class, we've only solved diffusion problems. And so all that we've been modeling is just kind of this passive spreading of whatever we're looking at. Okay. So convection is fundamentally different. And so convection, we're still transporting a quantity. We're still transporting something. But instead of letting it passively spread out over time, we're kind of forcing it to happen with an airflow. Okay. Okay. Fluid flow. Okay. Okay. Right, so that's the difference between them. And so are there any questions on any of this so far? Okay. One key difference that I want you to notice, before we jump into the numerics, is that when you have convection, there's a distinct direction associated with it. Okay, and so convection always flows in whatever direction the fluid is flowing, right? And that's something that's a lot of times that's something that you choose, right? So whatever way you choose the air to flow, the material is going to be transported in that direction no matter what. For diffusion, there is no direction, right? So diffusion goes in all directions equally, okay? And that difference in that convection has a direction to it and diffusion does not, that's going to play a key role in how we actually discretize it, okay? Okay.
Quick question.
Yeah.
By transport of material, are you just saying material as in like matter or like energy?
Yeah, it could be anything. And so yeah, it could be, in this case it's matter, and so we have mass transport of the air freshener, but it can also be for like heat and energy as well. Yeah, so the same concept applies for energy. So you can have a convection of heat, or you can have a diffusion of heat as well. Yeah. Okay. And so keeping those things in mind, and so keeping in mind the fact that diffusion spreads in all directions, let's see how that concept is reflected in our finite difference. Okay. All right, and so remember the key diffusion term is the second order derivative. Okay. When we replace this with a finite difference approximation, what we had was something like this. Right? So we have phi I minus 1 minus 2 phi I plus phi I plus 1, okay? All divided by delta x squared, okay? Let's ignore the delta x squared for a minute, and I want to focus on what's in front of all these terms, okay? Because if I draw this as a line, right? And so let's say that in the middle here we have node I, and so node I here being our node of interest. We have I plus 1 on the right, and so that's our right neighbor. Okay, and we have I minus 1 on the left, right? And so if I take these coefficients as weights, okay, bless you, right? We're just going to ignore the signs for a minute because I'm interpreting these coefficients as weights. Okay. Right, and so if we take the coefficients as weights, and we can see that we have a weight of 1 on our left neighbor, a weight of 2 on our central node, and a weight of 1 again on the right node. Okay. Let me do this. Let me imagine this is a seesaw. Okay, and so let me draw a pin support on our middle node right there. Okay. And so with the weights as they currently are. How would you expect the seesaw to move, right? And so is it going to dip in one direction or the other?
Balance.
It's balanced, right? It's perfectly balanced, as all things should be, right? And so, in other words, this finite difference scheme that we're chosen is perfectly balanced on for all of our neighbors, right? Okay. And that makes sense, right? Because the diffusion doesn't pick a direction, right? So diffusion just spreads equally in all directions. So that's what diffusion does. And so it makes sense that the finite difference scheme that we've chosen for this also does not necessarily weigh one direction over the other. It's perfectly balanced for all the neighbors that are associated with it. Okay. And you can say the same thing for 2D as well. And so I'm not going to draw it out for 2D, but if you took our diffusion terms in 2D and you wrote out all the weights for all of the neighboring nodes, what you'll see is that they're all equal. Okay. Because diffusion occurs equally in all directions. Okay. And so for diffusion, we kind of did it by accident. And so we weren't really thinking about this when we were doing it, for the last couple of weeks. But we ended up with a numeric, we call this a numerical scheme that matches up very well with the physical, behavior. Okay. And usually if you have this kind of matching, this kind of synergy between the numerical scheme and the physical behavior that it represents, then you're usually going to get good results because the numerics are going to reflect what's actually physically happening. Okay. Any questions on this?
What's the FD again?
FD is finite difference. Yeah. Okay. All right, so that's diffusion, and so all that is good. And so I bring diffusion up again, not because there are any issues with it, but just to illustrate that this is a good case. Okay. Now let's look at convection. Okay. Convection here is represented by a first order derivative, right? So we have d phi dx in the 1D case. Okay. And so if you remember, when we first started talking about finite differences, we have a lot of options for first order derivative. Okay. We have central difference. We have forward difference. And we have backward difference. Okay. And so let me do the same, let me make kind of the same seesaw plot here for each of these schemes. Okay. So let's start with central difference. Okay. So for central, we have d phi dx is equal to phi I plus 1 minus phi I minus 1 divided by 2 delta x. Okay. Okay. And so, let me go ahead and write the weights here. And again, I'm just going to ignore the signs because what's more important is kind of what the magnitude of the coefficients are. Okay. So that's central difference. Okay. Next, we have forward difference. And so forward difference, we have d phi dx is equal to phi I plus 1 minus phi I divided by delta x. Okay. And so for forward difference, you can see we have a little bit of weighting on the right side. Okay. Right, and then finally, we have backward difference. So backward difference is also a little bit lopsided. It's lopsided towards the back end. Okay. And let me do this too. Let me remind you what the level of accuracy is for each of these schemes. Okay, so for central difference, remember this was second order accurate. Okay. Forward difference was first order. accurate. Okay. And backward difference was also first order accurate. Okay. And so in terms of accuracy, it makes us want to use central difference because we always want to have the most level of accuracy for the least amount of work. And central difference here seems like the winning candidate because we're doing basically the same amount of work as forward and backward difference. And so in all cases here, we're only polling 2 nodes, right? But if we arrange the nodes such that it's balanced, then we get much better accuracy for central difference. And so, the tempting thing here, the tempting thing to do here is to use central difference for our convection term. But of course, the way that I'm saying this makes it kind of seem like that's not the best choice. I'll go ahead and explain why in a second. Okay. Any questions on any of this so far? Okay. All right. So let me go ahead and write that down. Terms. In terms of accuracy, central difference seems like the best choice. But unfortunately, accuracy is not the only consideration that we have when we're developing these numerical schemes. And so one other factor that we'll learn that kind of is as a result of convection is stability. Okay. And so what do I mean by stability? And so, probably when you think of stability, you might have seen that in other classes, in terms of mathematics. Right? And so I think, stability in numerical schemes, and this is not unique to finite difference. Every numerical scheme, suffers from stability problems, whether it be finite element, finite difference. Later in this class, we'll learn a method called finite volumes. They all struggle with stability. Okay, and so in a nutshell, what stability means is that it's the ability for a numerical solution to stay bounded and physical. Okay? It's actually a little bit difficult to give a good definition for stability, although that's kind of the best that I can do. It's a lot easier to describe what an unstable solution is, or what instability looks like. And so usually if you have an unstable solution or instability, instability in a numerical solution is characterized by wild and unphysical oscillations in your solution. And I have a good example to show you what that means in a second. And in extreme cases of instability, what's going to happen is that your solution is just going to return just literal garbage. Okay? And so you guys have probably used MATLAB before, and you've had situations where MATLAB returns not a number or nans. And so when you have an unstable numerical solution, that's what MATLAB will basically return to you. It's like a bunch of not a numbers it'll say the solution diverge or things like that. Okay. And from a practical perspective, as you'll see if you kind of continue this line of work in your profession, you're probably going to be grappling with instability a lot more than you will be with accuracy, because an unstable solution kind of makes itself clear very, very quickly. And if you show, like, say, your manager an unstable solution, they will not be happy because it won't be useful. Okay. And so let me give you an example of what an unstable solution looks like. So let's do an example. Okay. Okay. And so let's solve for the solution to the following problem. Okay. So let's say we have a diffusion term, and so let's say we have 3 d squared phi dx squared is equal to 75 d phi dx minus 8x. Okay. Let's say that we have two Dirichlet boundary conditions in this case, just because let's keep it simple. And so let's say that phi at 0 is going to be equal to 0, and phi at 1 is equal to 1. Okay. So these here are boundary conditions. All right. And so since this is a 1D problem, we can solve this analytically, right? And so we can solve this using pen and paper methods. I'm not going to go through the work of that because it's kind of torture, and I think we're up to torture today. And so I'm just going to give you the solution for this. Before I do, let's go ahead and identify the different terms of this expression. Okay? And so this term right here, because it has the second order derivative, this is our diffusion term. Okay. This term right here, because it has the first order derivative, this is our convection term. And then this last term, and so basically any term in a differential equation that doesn't have phi in it, that's going to be your source term. Okay. Right, and the thing to note here is this coefficient out in front. Okay, and so the number that's in front of the convection term, or the coefficient there, this is our convection velocity. Okay. Right. Remember, we talked about before that convection is a forceful transport of a material, via a moving fluid. Right? And so that fluid that you're using for convection has to have a velocity, and so that number right there is exactly its velocity. Okay. All right, and so after some work, and if you're curious about how how I got the solution, I basically used the characteristic equation, and so I formed a characteristic equation for this problem, and I used undetermined coefficients to solve for the non-homogeneous solution. Okay. So after the magic of math, okay, what we obtain is the following solution. Okay. And so we have phi of x is equal to 589 divided by 625 multiplied by 1 divided by e to the 25th power minus 1 multiplied by e to the 25x minus 1 plus 4 over 75 x squared plus 8 over 1875 x. Okay. So I think when I wrote this example problem 3 years ago, I was cursing myself because of how long it took to get this answer, because it was not fun. And so the plot of this solution looks like this. And so our solution here starts at 0, and then we have a sharp rise just like that, okay? And so this is 1 right here. Okay. And so I'm going to show you a MATLAB plot where I plotted this, but that's essentially what it looks like. Okay. All right, so what are we observing here? And so, what do we see from this plot? Remember, we have convection in this case. And so remember, convection means that, we have essentially you can think of it as like wind or water that's blowing in that direction, okay? And since our convection velocity was positive, that means it's flowing from left to right, okay? And so that kind of explains why most of the plot is kind of smushed over to the right, because all of the phi is being pushed on that side, okay? And so that's kind of the reason why we have the shape as it is. All right, any questions on this so far? Okay. All right, so that's the analytical solution, and that's kind of the interpretation of the graph. Now let's go over the finite difference solution. Okay. And so for the finite difference solution, remember, we're going to start with the original equation here, okay? And then every derivative, we're just going to replace with the finite difference approximation, okay? And so let's start with the diffusion term. And so for diffusion, we have a 3 out in front, and we're going to replace it with our usual diffusion finite difference, right? Okay. So this guy is our diffusion term, this in finite difference form. Okay. Next, we have our convection term. And so now we have a choice. And so, we have a first order derivative here, and we need to replace it with a finite difference approximation. For now, even though I've kind of been, foreshadowing that this is not a good idea, let me use central difference here for the convection derivative. So this right here is convection using central difference. Okay. And of course, we have our source term. Okay. Okay. All right, and so we've taken our original differential equation and we use finite differences and we've converted to an algebraic equation. Okay. Okay, so let me go ahead and let me simplify this a little bit. Okay, and so let me divide this entire equation. Okay, I'm going to divide this entire equation by 3 over delta x squared. Okay, and so that's going to get rid of this exponent out or coefficient out here. And so on the left-hand side of the equation, we have phi I minus 1 minus 2 phi I plus phi I plus 1. Okay. On the other side of the equation, we're going to divide it by 3. And so 75 divided by 3 is 25. Okay. 25 divided by 2, because we have another 2 right there. Okay. And then we're going to multiply this by delta x squared. And so that delta x squared is going to cancel out with 1 delta x. And so we end up with just a delta x over here. Okay. Then we have phi I plus 1, phi I minus 1. Okay. And then for the source term, we have just an 8/3 delta x squared multiplied by xi. Okay. All right, and so I'm gonna rearrange this a little bit because the best way to kind of arrange these equations is to take all the terms with phi and then put them on the same side of the equation. Okay. And so I'm going to take this expression and subtract it, and so it ends up on that side, okay? And so if we do that, we get phi I minus 1 minus 2 phi I plus phi I plus 1, okay? Minus 25/2 delta x phi I plus 1 plus 25/2 delta x phi I minus 1, okay? This is equal to minus 8/3 xi delta x squared. Okay. Okay. All right. Last thing I'm going to do is I'm going to take all the phi terms on this side of the equation and combine the like terms. Okay. And so if I do that, we end up with the following coefficients. And so for the phi I minus 1 term, we have a 1. We have a 1 plus 25 divided by 2 delta x. Okay. And then we have a minus 2 phi I plus a 1 minus 25/2 delta x phi I plus 1. This is equal to 8/3 xi delta x squared. Okay.
Still carrying the negative on the source or
Oh yeah, I am. Sorry about that. Yeah, I just missed that. Yeah, there's still the negative on the source term. I just forgot to carry it down. Yeah. Okay. And so through this work, what we end up with here is this is the finite difference equation for this problem. Okay. And all of the coefficients here for the phi terms, and so let me circle this, and this. Okay. And so all the terms I've circled in green, when we go to implement this in MATLAB, those are the terms that end up going into our left-hand side matrix. Okay. And I have a code prepared where I've kind of shown you how to do this. Okay. All right. And so, let me kind of take a step back here. So at the beginning of class, we talked about, the midterm for this class. And so what I just went through right now, where, I took a differential equation and I've replaced the terms with all the finite difference approximations, and I kind of worked through the math. Okay. And this is kind of what I expect you to do on the exam. And so this whole example right here.
So that would basically be our final answer for the exam.
So I might ask you to one step beyond this, and I might ask you to say, if I give you a grid of 5 points, use this equation right here to come up with those 5 equations for the 5 points. And so that incorporates some of the boundary conditions as well. Yep. And so you plug in for different values of I into this equation in order to get those algebraic equations. Okay, any questions on this before we look at the MATLAB code? Yeah.
so on the exam, should we expect a problem of this? Because obviously we didn't solve the problem itself, or should we expect something that difficult in terms of?
Yeah, this is a good level for the exam.
Okay.
Yeah. Mhm.
I have a question.
Sure.
Going back to the plot you showed us.
Yeah.
So you mentioned it's kind of like pushing everything to the right.
Yeah.
Is that because we have a positive velocity?
Exactly. Yeah. And so because we have a positive velocity, you know, it's a positive 75, then it's going to be pushing everything to the right. Yeah. Mhm. Okay. And so now we're kind of set to plug this into MATLAB. Or actually, first let me write down the boundary condition terms, just because those are really quick. All right, so the boundary condition equations, remember they were both Dirichlet boundary conditions. And so we had a Dirichlet condition at x is equal to 0. And so a Dirichlet boundary condition means that, you know, we're setting the solution value equal to that number. And so in this case, we have phi1 is equal to 0, because phi1 is the leftmost node in our domain. And then the other boundary condition was that phi at the right-hand side of the domain, which is the rightmost node. And so I haven't told you how many nodes that we have yet, and so I'm going to leave that in terms of big N. Okay. And so that boundary condition is going to be just, you know, phi at n is equal to 1. Okay. Okay. And so now that we have the finite difference equation and we have the boundary condition equations, you know, we're ready to implement this into MATLAB. And so okay, so I wrote to be continue because I need to swap to the computer screen for this. But is anyone still writing any of this down before I swap to the computer screen? Okay, so let me go ahead and share my screen here. Okay, so can everyone see my my screen? Okay. Okay. All right. And so you know, here I basically set up the code. And so you can see here that I'm assembling the linear system. And so I've actually broken it down into two different parts of the code. Okay. And so just like before, just like you've seen with diffusion, I'm using a loop here to construct the matrix. Right? And so you can see here that I have a section of the code here that's going to be for the diffusion terms. And so you can see here we have our typical +1 on the left and right neighbors, and we have a -2 on the central node I. And then we also have the convection terms for this equation as well. So because we're using central difference, you can see here that we have a contribution on the left neighbor, and so that's I -1, right? Okay. And we also have a contribution on the right neighbor as well. And so those are equal to 1/2 times the velocity. And so our velocity here you can see is 75. Okay. Multiplied by dx, which is the grid spacing, and then divided by visc, which is our diffusion coefficient, which remember was 3. Okay. All right. And so for this first case, I'm going to solve it with n is equal to 7, and so we have seven nodes in our grid. Okay. And I've also plotted the analytical solution as well. Right. All right. So let me go ahead and run this code. And so you can see here that's this is what the solution looks like. Okay, let me go ahead and make this a little bigger. And so in blue, or let me say, so let's start with red. So in red, that's the exact solution, and so that's that's the equation that I plugged in exactly from the notes. Okay, so that monstrous kind of equation that we solved by hand. And then in blue here we have the finite difference solution. Okay. And so what do you notice about the finite difference solution? It's a little bit it's not chilling. And so it's kind of bumping up and down right here. Okay. And so, when you see a finite difference solution and it's having these kind of wild oscillations like this is a good indication that your solution is unstable. Okay. Remember, instability is characterized by these kind of crazy oscillations, and this is kind of what it looks like. And, the thing with instability that it's a lot easier to show rather than it is to than to just talk about. Okay. And so these are bad because you can see that the exact solution doesn't do this at all. So the exact solution is this kind of nice smooth curve that kind of goes up like that, whereas the finite difference solution is bumping up and down. Okay. The mouse is unstable. Yes, it is unstable. Yeah. Yeah, they need to get me a mouse with better DPI here. It's this one's not there. But also my handwriting with the mouse is pretty bad. Okay, and so this is bad, and so we don't want this to happen. Okay. And so if you do see this, there's a quick fix that you can do for most cases. And so for a lot of cases, if you do have an unstable solution, one thing that you can do is you can simply increase the grid resolution. Okay. And so instead of 7 nodes, let's try with 50. Okay. And so we have we're going to solve it with 50 nodes. And if we run this code, you can see here that our instability problem is fixed, right? And so you can see here that our curve is a lot smoother, right? Maybe it has a little bit of inaccuracies right here, okay? But for the most part, it's mostly fixed. And so there's no longer any big oscillations, okay? And so, this is kind of I would say for the user, for the engineer, this is an easy way to fix instabilities. This is just, we call it refining your grid. And so if you increase the number of grid points, or in other words, you're reducing the value of delta x, which is the space in between grid points, then you can fix a lot of the instabilities. And so, you might be thinking, why don't we just do that all the time? And so, because we already know that when you refine your grid, when you increase the grid resolution, you're making your solution more accurate anyway. And so why don't we just always do that? Okay. And so it's a little bit hard to appreciate, because we're most going to be working with 1D and 2D problems. But refining your grid is not always going to be practically available to you. Because if you think about, you're doing 3D, like if you're doing 3D problems, 3D simulations, and you refine your grid, that's often going to be a huge increase in your cost. And so, that's going to be the difference between waiting maybe an hour for your simulation to finish to maybe waiting 10 hours, right? And a lot of times you don't have that long to wait, especially if your manager wants answers kind of right away. Okay. And so a lot of times refining your grid is not always going to be available to you. And so we have to come up with different ways that we can formulate the problem, formulate the finite difference, so that we can still get a stable solution, maybe at the cost of some accuracy. Okay. Any questions on this?
Will you be uploading this code?
It's uploaded. And so it's if you look on the course website, you go to files. So all the code for the class I've already have uploaded here. And so the one that I just went over right now is actually the very first one, which is 1D convection diffusion. I call it class activity, but it's more a demonstration than a class activity. Yeah. I meant to do this before the class, but I'll link this onto the weekly page as well, so you'll have it available for you. Okay. Yeah.
Do you mind in your code have the Computational diffusion term?
Yeah.
Explaining the syntax of it.
You mean why I divided by this diffusion term here?
No, for instance, the 24th one.
Yeah.
So you repeated the one that you're trying to assign.
Yep.
And then you subtracted 2.
Oh yeah. So this is our update. This is our update notation. And so what this says is that what we're saying is that the new value of this entry is going to equal to what's already there. Right, so this is the old value of what's in that matrix minus 2, and so this is a way to say that and so the reason I do this is because I'm making kind of multiple lines here, and so when I do this convection term line, and so you can see here I'm doing the same thing for A, I comma I minus 1 is the same entry as right here. And so I don't want to overwrite this. I just want to add to it. And so to do that, I use this notation to say that, I'm going to take what's there already and then just add to it. And so I just repeat that same syntax for all of them, just to kind of be consistent with that.
And since we started at 0, it's basically that outline right there would be 0.
Exactly. Yeah. So actually for the diffusion terms, these are kind of unnecessary. And so you can kind of get rid of them because it's the first line. But it's kind of just consistent to kind of just have it all throughout. Okay. Okay. Any other questions on this code before we come back to the notes? Okay. All right. So let me go ahead and stop here. Okay, so let me go ahead and summarize. And so with sorry about that. Okay. And so if we use a central difference scheme for the convection derivative in our equation, then there's a possibility for our solution to be unstable if the grid is not refined enough. Okay. All right. And so before we talk about kind of the better way to do this, I want to talk about this first. Okay. And so how do we know if the grid is refined enough? Okay. And so one thing you can check is something known as the Peclet number. Okay. And so the Peclet number, the way you compute it is you take u multiplied by delta x and you divide by k. Okay. Where u here is our convection velocity. Okay. Delta x here is the grid spacing. Okay. And k here is our diffusion coefficient. All right. And so for a lot of problems, that you're gonna find, a lot of times the convection velocity and the diffusion coefficient are more or less fixed, right? And so those are going to be given to you in the problem. And so usually what you have control over is the grid spacing. And the way that you control the grid spacing is by specifying the number of grid points in your grid. Okay. And so in order to have a stable solution, this Peclet number has to be less than 2. Okay. And so for a given problem, depending on the convection velocity and the diffusion coefficient, if you can set the grid spacing such that the Peclet number is less than 2, then you're going to have a stable solution. Okay. And so if we go back to the previous example, right? So for the previous example, we had u is equal to 75 and k is equal to 3. Okay. And so our Peclet number was equal to 25 times delta x. Okay. And so to get a stable solution with central difference, then our grid spacing must be at most 2 divided by 25. Okay. And so if you're adamant on using central differencing for your convection terms, which is not a bad thing, right? Because if you can get the solution to be stable, then your solution is going to be second order accurate off the rep, which is a good thing. Okay. And so it's not a bad idea to use central difference for convection. It's just that you have to make sure you have enough grid resolution in order to cover it. Okay. And the way that you find out if you have enough grid resolution is by computing the Peckway number. Okay. Give me a second. Hey guys, do you mind keeping it up a little bit? I got 10 more minutes.
What if there's no convection?
If there's no convection, you don't have to worry about it. So if there's no convection, then you're going to get a stable solution no matter what. So convection is the thing that makes it go unstable. Yep. Okay. So what if you don't want to do this? And so what if refining your grid to lower the Peckway number is not an option for you? And so what you can do instead is you can use a different scheme for the convection derivative. So let's do this again. And so, remember we started today talking about how, when we modeled diffusion, the finite difference scheme that we chose was a good match for the physical phenomena, right? And so in other words, our diffusion finite differences weighted both sides equally because diffusion is kind of an equal spread in both directions. Okay. And so let me do the same thing. And so let's draw our convection term. Okay. Okay. But on top of this, let me do this. Okay. Right. And so remember what we talked about at the beginning. So the thing that's different about convection compared to diffusion is that there's a direction to it, right? And so convection, doesn't just go in equally in all directions. It goes in whatever direction that the velocity is pointing. Right? And so if the velocity is pointing from left to right, that means that's the direction where we're going to transport. Okay. And so if we use our central difference scheme, okay. Remember, the whole point of the central difference scheme is to compute what the derivative is at this location. Okay. Okay. The problem with this lies in this guy right here. Okay. Because when you have a directionality to your physics, right? And so in other words, we know the physics is traveling from left to right. What we're basically saying by having a weight of 1 right here is that in order to find the derivative at our node of interest, we're trying to get information, or we're trying to obtain information from a place that the velocity hasn't even traveled yet. Okay. because it's downstream, right? And so if I can characterize these locations in terms of, you know, where they are in terms of the velocity, this would be upstream, right? Because that's where the velocity is coming from. And this would be downstream, right? And so another way that you can interpret convection is that, you know, is that we have kind of a not only a direction of transport, but also a direction in which what I like to call information is flowing. And so information here is flowing from upstream to downstream, okay? And so it makes more sense for us to put more weight on the upstream side. Okay? Okay. All right, any questions on this? Okay. Okay, and so with this in mind, that, you know, we would want to place more weight on the upstream side, which of our finite difference schemes actually puts that weight on that side? Would be our backward difference scheme, right? Okay. And so let me go ahead and draw the same line. Okay. So we have d phi dx. We have velocity going that way. Okay. So our backward difference scheme had more weight on the back end. So we had a weight of 1 on our left neighbor and a weight of 1 on our own neighbor, okay, or on ourselves. Okay. And so because this is kind of a lopsided scheme on one side, you know, this is much better suited to simulating convection, you know, with velocity going that way. Okay. Okay. And so we don't have enough time to see this, but, you know, if you take this approach and you apply it to our script, okay. And we apply it for the case when we have 7 grid points, right? And so remember, when we tried this with 7 grid points for the central difference, we ended up with an unstable solution, okay? And so if you try this for, you know, with the backward difference scheme, okay, what you'll end up with is the following. So I'm going to use the same color scheme as the code, okay? And so remember, our exact solution looks like that. And what you'll get is a finite difference solution that looks like that. Okay, so in the blue right here, we have finite difference. Okay, and in the red, we have exact. Oops. All right, and so, you know, I drew it with the gap on purpose because that's what you're going to see. And so it doesn't, you know, it doesn't look great. And so, you know, of course, you would like to see the two matching a lot better, you know, but at the very least, this solution is stable. Okay. Right. And that's a good thing. And so if your solution is stable, at least you can work with it. Because if your solution is showing any kinds of instability, then what you kind of have to do is you kind of have to throw just the whole thing out. And so, you know, given the choice between, you know, a solution scheme that's stable versus one that might be more accurate but can be unstable, most of the time people are going to go with the stable one, because at least with the stable solution you can actually work with it. Yep. All right, question. So would we use a factor coefficient to state that it was an approximation solution if we were to use this system for a real world solution? Yeah, I mean, there's always that caveat whenever you are working with a numerical solution. You know, there's always going to be a caveat that this is a simulation, and a lot of times you don't have access to what the exact solution is. And so, you kind of have to do your best with, refining your grid and making things as accurate and as stable as you can. Okay. Right. So one last point I want to make about this is that, kind of the trade-off that you make here that you can kind of see is that, you got a stable solution, but it's only first order accurate. Okay. And so that's kind of unfortunately the world that you live in with numerics is that, there's always kind of a trade-off. And so if you want more of one thing, you're going to have to pay up in another area. And so that's the trade-off that we make here. So in order to get a stable solution, we paid for it by having a somewhat more inaccurate solution.
So the central uses second order?
Central is second order. And so if you can get it to be stable, the central order is the most accurate. But if you want just a stable solution, then this one's this one's better.
So the only way to get it stable would be to second order accurate, that you would only have to use the central difference.
That's right. Yeah. Yeah. So the only way to get the second order accurate is to use the central difference scheme, but you have to be careful with the grid space there. Yeah. Sorry. One more point. And so this is all assuming if you have a positive convection velocity, right? If you have a negative velocity, right, then that changes things. And so if you have a negative velocity, now the velocity going from right to left. And so the scheme that you use for this one is a forward difference instead of a backward.
So it's the same as the backward, just flip.
Exactly. And so you always want to place more weight on the upstream node versus the downstream. Okay. All right. Oh, question.
Yeah, like, so if we use a forward difference, would our finite difference plot be on the right side of the event?
Yeah. So if you have a forward difference scheme, then then the exact solution is going to be different because the velocity is going the other way. You can try that out actually. So you can look at the script that I uploaded, and then just put the negative velocity, and then kind of see what that looks like. Yeah.
And since this is stable, we can use less amount of grid points than essential difference. But if we were to increase the grid points, could we get it more exact?
Oh yeah. And so even for a first order accurate solution, if you refine the grid, it's going to be more accurate. It's just going to take a little bit longer to get like exact matching because it's only reducing by a first order factor.
But it would still be better options.
So usually the logic goes if you have a coarse grid, it's better to be stable, so to use a first order method. But if you can refine the grid a lot, then central difference is better, just so you get a more accurate solution. Okay, all right. So I'm a little bit over time, so I apologize for that. So thank you everyone for coming today. It's the only time meeting this week, so have a great weekend, and I will see you next week.
Yeah,
Thanks, guys. Have a good weekend.
Dr. Tran.